And for our final talk, this session, we're going to move from the hardware world into the world of sparsity. And Avery is going to tell us about how equivalences are useful in that domain as well. So take it away when you're ready.
Okay, let's see what happens. Okay, perfect. Awesome. Yeah, so my name is Avery, and I'm excited to be presenting our tool spec. So yes, sparsity is very much in the name, and so is equivalences. And so today I'm actually going to focus on the equivalences part that's relevant to eGraphs. And if you're interested in all of the details about sparsity, tomorrow I'm focusing only on that at the Sparse workshop, I think at the same time tomorrow. So you can check that out if you're interested. And if you want the mix of everything, then I'm doing a talk on Wednesday with the mix of everything. But first of all, I just want to, like, right off the bat, let everyone know, okay, here is what we're trying to do. This is the main goal. The idea is you have some input code. Like this is a matrix multiplication example taken from Polybench. And the motivation is that general purpose compilers, they should focus on compiling, and you shouldn't necessarily rely on them to optimize this kind of code in the best possible way. They'll do a decent job, pretty good job, but there's like a ridiculous amount of work that's been done in these particular domains like matrix multiplication, like numerical codes, simulation codes, and everything, where people have, you know, optimized it as much as possible. And so maybe a better thing is to step back and just say, hey, this is, I know what this is doing. This is a matrix multiplication code, and here's how to translate it into, you know, a library call for a GPU, for example. So this is the main idea, is about extracting out segments of code that we know map to very efficient library implementations or DSLs, and let those tools take care of the optimization and do exactly what they're made to do. So this is the whole pipeline of SpEQ end to end. And so you could see the beginning diamond part and the equivalence check part. That is the stuff related to sparsity. And so if you're interested in you know, Z3 and K-induction and all that kind of fancy stuff, then I'll talk about that tomorrow. And today I'll focus on the part that's more general. It doesn't, is not necessarily specific to sparse or dense. It's just about trying to find these examples in code. And just to give an idea of what can be done in this domain, I have 3 benchmark examples. One is a histogram code pattern, one is a matrix multiplication code pattern, and one is a reduction code pattern. And these are, you know, found all over the place in lots of different types of codes. And if you, this is the kind of performance that you can achieve by just, you know, taking the compiler out of the equation entirely. So in this example, we have 3 different, I'll call them backends that we use. So one of them is, we're kind of calling the DSL is OpenMP. In a sense, OpenMP is kind of like, you could argue, a DSL. And then MKL and cuSPARSE / cuBLOS for dense codes. Those are the libraries that we offload to. Okay. So now what I'll do is just go through the pipeline and explain each step by step, yeah, how SpEQ works. Okay, so SpEQ operates on the LLVM IR, and so sometimes I'll like switch between a source code representation or an LLVM representation, but just keep in mind that everything that's going on, it's happening on LLVM IR. And I can't show, you know, the whole example because that would be pretty crazy. So I'll focus just on this inner loop here. And if I give this to an LLVM front end, like in C, for example, would be Clang, then I'll get, for the inner loop, an IR that looks like this. It has at least 3 blocks. So the first block is the pre-header, and we're guaranteed that this block exists because we do a loop rotate pass, and that guarantees this block will always be there. And then we have the body block, which contains some instructions, and then there's always going to be at least one exit block. So in LLVM, the vast majority of the instructions, they take some arguments and they return some value. And that's great because you can imagine how that would be like fairly easy to map into representation. You could put it in eGraph. But the problem comes up mainly when we start to talk about memory, because this example instruction here, the store, it's computing a value. So here, like Cij plus alpha times Aik times Bkj, and it's storing it at Cij, but it's not returning anything. And the reason for that is because LLVM has just like a mutable model of memory, where you just mutate it and then it's updated, and you don't get anything back. But we would like to get something back. Yeah. So what we do is we actually use some of LLVM's analyses to assign different versions to memory. So the notion here is like when you do a store to memory, you get back a totally new version of memory that's an exact copy of the original, except at that one location, it's been updated with the value that you stored there. So that's shown by the red text, the memory phi and the memory def instructions. So I'll briefly explain what those mean. The memory phi instruction, you can think of like a join point. It's basically choosing a value based off the control flow. And the more interesting instruction that you most commonly see is the memory def. So you can think the memory def is like taking C3's version, so like version 3 of C, you could imagine, and it's returning version 2 of C. So now we can like augment all of these memory stores as imagining, okay, maybe they have an extra implicit argument and an extra return value, which is the memory version. So now let's imagine that this store instruction, is additionally taking memory version 3 and is returning memory version 2. And then that gives us a handle that we can use to refer to it inside of a term. This term is, part of it is represented here on the right-hand side. And I have to leave a lot of the details out. So, of course, all of these will be in their own E-class. And everything except for the leaves of the term is going to be some sort of function symbol. But here I just want to give an intuition for like what kind of structure you get from this translation process. Okay, so that's the bulk of the idea. There is some extra detail that's a bit interesting when we're translating the IR. So, of course, these phi instructions are going to be very common in LLVM IR, and probably like most people have some notion of that or maybe some experience with it, but if not, I'll briefly explain. So because LLVM uses the static single assignment form, it means every register is only going to be assigned to once. So if you have this kind of program that has the branching structure, like the diamond branching structure, where in one branch I assign 1 to B, and in the other branch I assign 2 to B, then I'll have the case where I can only assign to B once. So I need this special instruction that will let me choose the correct value based off of which branch I visited. So you can see that phi instruction in block B4, which is saying, okay, if I came from block B2, I should have value 1. If I came from block B3, I should have value 2. So the issue here is that when you're looking at the phi instruction, you don't immediately know, okay, how should I be choosing this? Like, where did my comparison come from? Where is this branch condition? It's not totally obvious from the IR. So the idea here is that we have to do a bit of extra analysis to extract that branch condition A. And the way finally it's represented as a term is as this like f function that takes A as an argument, and then it will return the proper value depending on A. Like, for example, if A is true, then it will represent 1, and if A is false, it will represent 2. And the idea is that this if function is like the same as B, like they become the same thing. Okay. So now I'll talk about how we actually do this matching, how we recognize that the input program is equivalent to some, very fast implementation that we can map to a library. So what we do is we have like a library of different reference implementations, and these can be in any source as long as there's a front end to get to LLVM IR. So in SpEQ right now we have gem, we have matrix vector multiplication, histogram, and reduction, and all of those reference implementations are just provided in like C source code, and you can write them in just kind of a straightforward high-level way. For example, the histogram reference is like maybe 3 lines. It's just like a for loop with one line in the body. So it's very easy to add these reference implementations. You just give a C file. And the idea is that we take these reference implementations and we turn them into rewrite rules, so that we can ideally take the input code and rewrite it directly into a function symbol with the same name as the reference implementation. That's how we recognize, okay, this is equivalent to the reference implementation. And then on top of that, there are some, like what I'd call generic rewrite rules. Here are some examples for arithmetic, to try to make it a higher probability that the input program is going to have a path of rewrites into the reference implementations. So beyond just these arithmetic examples, we have a couple for loop level transformations and a couple for if level transformations. So these are like the arithmetic ones I showed previously. Then we have fusion, interchange, most of the very common loop transformations. And one that's slightly less common is what's called merge. And this is mainly to target tiled codes. So if there's a code that's already been tiled, and or vice versa, and you want to detile it and or tile it, then well, this one is actually one way. But if there's already a tiled code, then we can detile it, I guess. And this kind of de-optimization thing is a hint for the next slide, which is another trick that we employ to make it more likely to get input code matching reference implementations. And so on the top I have this scenario where what's happened on the right-hand side is that somebody has done a transformation to store the intermediate result of the loop in a scalar instead of writing to memory all the time. And this is a really, really common way to write code. And if I wanted to write a rewrite rule going from left to right, that would not really be a straightforward thing to do, because I have to introduce this dot scalar, which is like a new variable. So you could imagine the case where my reference implementation is written in the way on the right, and my user input code was written on the way on the left, and now there's absolutely no way to transform the input code to the reference implementation. But of course, we can always go in the reverse direction. We can throw away the dot, and we can of course, like this is from an optimization point of view, not a good thing to do. But from like a recognizing code point of view, it increases our coverage. So actually, what happens is instead of like one reference implementation creates one rewrite rule, we actually create a class of rewrite rules for every reference implementation, based off the existing rewrite rules that we have. Okay, so that's how we get all of the actual rewrite rules that get used. And the final step, once we actually have the for each reference implementation itself, like how do we get from that to an actual rewrite rule, the process is pretty straightforward. So basically the left-hand side of the rewrite rule is the function body. So this is the reference implementation function body. And every time we encounter a function argument, like a parameter to the original function, that becomes a placeholder in the left-hand side rewrite rule. And the right-hand side rewrite rule is just a function symbol with a fresh name for the reference implementation, and then all of the function arguments, function parameters as arguments to the function. So this part becomes the left side of the rule, and this part becomes the right side of the rule. So now we have all of our rewrite rules, and we want to translate our input code into a term that we can put in the eGraph so that we can apply those rewrite rules on the input code. So the term is created through the process, like the LLVM IR translation process that I explained in the beginning. And here is a slightly more complete version of the whole program. Again, there's like still some stuff omitted. For example, the types here are omitted. So this 0 is not going to be just a 0. It's going to be another function that is representing a type. And that function takes 0 as input to create that type, and so on. And the main idea is that the whole program, so like every loop, every instruction, it all just becomes like a single term with a single value that you could theoretically compute and collapse. And I also want to briefly explain the fold function. So loops are represented as folds, and they take an initial value. In this case, the initial value is a C array. And they have a body represented as a lambda. And I just want to be clear that there isn't like a lambda calculus implemented in the graph or anything. But the lambda here is used to represent the capturing of different arguments as well as the instructions related to those captured variables. So in this case, like C and I are captured, and then the body is another fold, and that fold has another fold as input value, and so on. So yeah, these terms can very quickly become like really big and really complicated, but I just want to give everybody like a picture of what it looks like. And you can look in the paper for more detail. Okay, so now we have our term, and we also have this gem function. And through the rewrite rule that we defined earlier, we can match the input code to this function, and that allows us to place them in the same equivalence class and show that, okay, our input code is, with this mapping of arguments, is the same as a gem. And there are lots of cases that can happen when you have overlapping reference implementations. For example, if you have a matrix vector multiplication and you have a matrix matrix multiplication, then you'll have the case where some of your subtrees will actually also be equivalent to matrix vector multiplication and so on. So sometimes people ask how that case is handled, and we have a very simple cost model to try to target, like, okay, what is the so-called like biggest operator? So gem is going to be bigger than MV and so on. But depending on the backend and depending on the application, you may want to have a different cost model. But that's like kind of future work for us. Okay, finally, you have the translation step. So for the sparse case, this is kind of more complicated, but for the general case where your code isn't sparse, this is pretty straightforward. You have a function symbol with the name that you care about, and then your backend decides how it should be translated. So if you're targeting cuBLAS, for example, and you say, okay, I found a gem reference implementation in this code, then it's just a few lines of cuBLAS library calls to do that translation and execute the code. Okay. So we have results across 10 different benchmarks. And the red bar, the runtime check, is related to, again, the sparsity stuff. So you can basically just kind of ignore that. And I think these results should not be surprising to anybody, right? Like if you're translating to a special library, you'll definitely see speed up. So I think the more interesting results are related to detection. So there are lots of other tools that will look for patterns in your code and try to do the same sort of translation technique. And the problem is that they all have quite large trade-offs. So there's codes that are very brittle, techniques that are very brittle. So they're not able to match a large diversity of slightly different codes. And then there's other tools that are so high level and so sophisticated that they're just so slow, and usually they time out and they can't actually find the codes. And equality saturation is a very nice in-between because it is limited, it is bounded. You don't have to run forever, and a lot of the space will be covered by if you have a decent set of rewrite rules. Also, we are usually pretty close, somewhat, to the LLVM 03 pipeline, even though everything is written in basically Python. Like we are using libraries written in Rust, for example, egglog. But we're still able to keep up with a lot of these tools. So unlike a lot of kind of verification, equivalence checking tools that can take a lot of time, we're not too bad in terms of latency. Okay. So yeah, this is a tool that is basically designed to recognize codes that you care about. If you want to add more codes to this tool, it's pretty easy to do that. This QR code is a link to the artifacts for SpEQ, and there's instructions there on a README on how to add your own reference implementations and how to add your own backends. So I think one of the ways this is going to be the most useful for people is, for refactoring, for trying to recognize, okay, I should have written it this way. I don't want to go through and rewrite everything. So, just find this and rewrite it to this for me. So if you want to do something like that, feel free to follow the link, download the artifact, and give it a try. And yeah, in the future, we're just planning on trying to make this more usable for people. And yeah, that's everything I wanted to talk about. So thank you.
All right, thanks so much. We have time for a few questions.
Thanks for the great talk. I have questions on both the sparse side and the equality saturation side, but I leave the sparse side for tomorrow. Okay. So for the equality saturation side, it seems actually somehow connected to the slotted graph talk. So what do you do actually to manage the scale whenever you're dealing with basically name bindings?
So, like I said about, I kind of hinted about it with when I was on this slide. This lambda is just a convenient name, and we're not actually doing anything with the lambda. So that is, we're not actually doing any like reduce rules or anything like that as rewrite rules. So in this case, we didn't run into too much problem with that. But one of the future directions we want to look into is, instead of just matching to implementations, to also actually synthesize new implementations that may not exist through equality saturation. And so in that case, even though we haven't looked into it, something like slotted eGraphs I think would actually help a lot. Yeah.
So as a follow-up, so in this case, I'm not sure whether the eGraph is complete or not, but I assume that somewhere in the eGraph, you should have the representation for C, I, J, and beta. And this means that actually you have to refer to the bindings that have appeared in the lambda side.
Oh, yeah.
So that would cause issues, because what happens if I have basically another code that doesn't use I, so it uses like I prime?
Yes.
And that could basically make it problematic actually to do the matching.
Yeah, good question. So it is problematic in the case you described. Yeah. The case, however, that won't necessarily, most of the time it's unlikely to happen in SpEQ, because the variables we care about, the variables that we match against in the reference implementation, are abstracted away as placeholders. So renaming it becomes not a problem anymore. Yeah.
Okay, and with that, we have one more question.
Thanks for the great talk. So I wonder what is specific to the sparse applications, since, for example, for GEM and GMV, they are very general for different applications, but not limited to sparse.
So imagine you have GEMV, but so it's doing an MV, but it's actually using CSR as a storage format. And you want to match that to a reference implementation, and you don't want to write a reference implementation for every possible combination of MV with CSR, MV with COO, MV with CSC, MV with ELL, MV with DIA. So instead, what you want is to decouple MV from CSR and match them separately. So that's what this branch is for.
Okay, let's thank everyone one more time.
Thank you.